Okay, so welcome to this first session of the second day of this conference. So our first presentation will be online by Tommy Hofmann. Tommy, I can see you're on.
Can you hear me?
Yes.
Good.
We can hear you. Okay, that's very good. Can you share your screen? Wonderful. Right. So this is to Tommy Hofmann, who's going to tell us about a software presentation or demonstration about computing Galois groups of Ehrhart polynomials in Oscar. Floor is yours.
Thank you. One quick question. How long do I have?
25 minutes, and then we'll have a 5-minute question.
I will try to skip a slide here and there. I guess you have a tight schedule. Okay, so thank you. Thanks to the organizers for organizing this conference. So what I present is joint work with Klaus Fieker and Michael Joswig. And when I talk about Oscar, this is also due to all the Oscar developers. Okay, so let's get started right away. So what are the main players from geometry I want to talk about? These are Ehrhart polynomials. Here's a quick reminder what they are so that we are all on the same page. So we take a lattice polytope, let's say d-dimensional, and then instead of counting the points only in P, we scale P by T, and in this way arrive a function which depends on T, and is the theorem of Ehrhart that in this way you get a polynomial in T of degree D, which we now call the Ehrhart polynomial. Here are two small examples. So if you take this hypercube in dimension D of side length 2, then you can just count the number of points. It's 2t plus 1 to the d. And this is already a polynomial. So this is the Ehrhart polynomial. Or if you take this Fano simplex in dimension D, so this convex hull of the d unit vectors and this negative coordinate sum, the Ehrhart polynomial can also be worked out by hand. It's this difference of binomial coefficients. So there are many things we know about Ehrhart polynomials. For example, leading coefficient is the volume, the constant term is 1. It's not integral in general, but you can scale it by d factorial. And for certain classes of polytopes, we actually know also a few things about the zeros of the Ehrhart polynomial. And for us, from an algorithmic experimental point of view, important thing is that you can actually compute this Ehrhart polynomial. It's a bit subtle, so not trivial. It might involve computing lattice points or triangulating your input. But anyway, for examples of interest, this is possible. Now, of course, many questions remain open. So the most ambitious one is, what are actually the polynomials arising as Ehrhart polynomials? Or what are exactly the roots of the polynomial? The question we asked ourselves is, what is the Galois group of such an Ehrhart polynomial? And morally, what is the Galois group? It doesn't say you exactly what the roots are, not where they are, but it somehow captures the symmetries between the roots. Now let me make this a bit more formal quickly. A quick reminder from your algebra course what a Galois group is of a polynomial. So you take a rational polynomial, let's say of degree D, and let's assume for simplicity that the roots are all distinct, so f is square free. So we get d roots in the complex numbers, and these the roots, alpha 1 up to alpha d should be, you can adjoin to Q. This is a normal extension of Q, it's finite. So it has a Galois group, let's say the full automorphism group, and this is what we call the Galois group of F. And such an automorphism is defined by what it does on the roots. So it will permute the roots. So this Galois group is always thought of as a permutation group acting on the roots. So we always think of the Galois group as a subgroup of a symmetric group. Here are 3 examples. So in degree 2, you always get the symmetric group on 2 letters. So a finite group of order 2. Here's the smallest example with Galois group S3. And in fact, it's a theorem of van der Waerden that if you take a random irreducible polynomial, it will always have Galois group SD. Now, I don't want to go too much into details about how to compute this, just few remarks, because there's an important conclusion to take away from this. So that you can do, you can play some ad hoc tricks for small degrees and special situations. And in general, there's a very efficient algorithm due to Staudu-Haar, which works for arbitrary degrees and can also be extended to arbitrary polynomials, so not necessarily irreducible. And the interesting thing is that if you look at this algorithm and you want to implement it in your favorite computer algebra system, you notice quickly that you will have to use tools from two different domains. So we will have to use tools from group theory and from number theory. So, and these tools are let's say non-trivial, quite sophisticated things that you have to do, but you have to have both of them available. And in our situation, if you want to do experiments with Ehrhart polynomials, we actually also have to have access to some polyhedral geometry in some algorithmic form. So we actually have to have access to 3 different areas to make this investigation work. So what are your options when computing Galois groups? So what are possible implementations? So first of all, the objects we are interested in, these Ehrhart polynomials, they have arbitrary degree and they are not necessarily irreducible. Sorry, it must say they may be reducible, so not necessarily irreducible. And then if you start up Google and look for possible implementations, you find out that GAP, which is a package for group theory, has an implementation for degree up to 15. Pari, which is an package for number theory, has an implementation up to degree 11. And Sage, which has access to both, you have the supremum of both restrictions. So important to notice, this is just group theory, this is just number theory, and in their own, they are not able to handle the general case. So they do some ad hoc tricks, pre-computed tables, but all they can do is, which is already quite good, that they have only functionality to compute with limited degree, but this is not sufficient if you want to investigate interesting families of Ehrhart polynomials. Now the 4th contender is Magma, which in fact has all the functionality that we want, arbitrary polynomials, but it has the minor drawback that it's closed source. So the first 3 are open source. Magma is closed source, which might not be a problem morally for most of us, but maybe the bigger problem is that it costs money. So it's still a few $100 unless you are in a very privileged situation where it comes for free. So not really an option if I want to just compute a few Galois groups. And what we report on is a new implementation and it's the first open source implementation for polynomials of arbitrary degree. And it also includes reducible polynomials, but the reducible part is not too important. The interesting part is the arbitrary degree part. And it's available in the new computer algebra system OSCAR. And since this is a bit about software, I will use the rest of the time to talk a bit about OSCAR, how it looks like in action, and let's say a few things we found out about Ehrhart polynomials in their Galois groups. Okay, so what is OSCAR? So it's a fancy acronym as usual. It stands for Open Source Computer Algebra Research System. So fancy name. It's funded currently by the DFG in 3 different stages over the range of 12 years. We're currently in stage 2. And here's our vision. We want to develop a visionary next generation open source computer algebra system, integrating all system libraries, packages developed within the TRR. So a lot of business, advertisement, language. I will come to this in a minute, what it means to integrate all the systems. What are all the systems? What is this TRR? Just two more things. It's built using the Julia language, which is an open source language that we thought was a good idea a few years ago, and we still think it's a good idea. So we don't write our own language, and we just piggyback on Julia for many things. For example, it makes the installation rather straightforward once you have Julia. And what is Oscar? Without this this vision statement, we consider it as a tool for interdisciplinary research in computations in algebra, geometry, and number theory. And this interdisciplinary part is what I also try to highlight or emphasize in this talk. We have this different areas, algebra, number theory, that you need to be able to compute Galois groups. And then we have this application coming from discrete geometry in our case. So we have different parts, and I think it's very important to have all the tools available to ask interesting questions and to answer interesting questions. Now, what are these tools that make up Oscar? So when we started, we already had different packages available, developed in Germany, founded by DFG partly. And the idea was to bundle them into one system. And this is what Oscar does. So the main players are Gap, Singular, Polymake for polyhedral geometry, and then some anti-component for number theory mainly. And so using Julia, we tightly integrate them in Oscar, but then we go, of course, beyond this. So we not only have access to these systems, but we use the systems to build more complicated things. So, and then what we're trying to do is we're trying to develop a very consistent, coherent system. All these things have different notations, conventions, so there's a lot of things to make consistent. But at the same time, one has always access to all the intricating details of each system. So, for example, you can call every function of Polymake, even if it's not already wrapped up in a nice way. Okay, so let's look at some examples. How does it look like in practice? So let's start with this cube, or let's say it's a square in dimension 2, and we want to define it as a point satisfying this inequality axy less or equal b. So how can you do this in Oscar? So you define a matrix, just specify the columns, the rows separated by semicolons and this vector, and then you can just create this polyhedron by providing the matrix A and the vector B. And then we can count the number of points or look at the points, lattice points, and there are these 4 points as we expected. So this is good news. It's doing something useful. Now let's compute the Ehrhart polynomial. Let's do it first by hand. So recall that we have to count the points after scaling p. So what we do is we do this, we form this list. So we scale p by t for t in 1 to 5 in this interval, take the lattice points and take the length, meaning counting the lattice points. And then it's not surprising, we get these square numbers, 4, 9, 16, etc. Now we know the Ehrhart polynomial interpolates these values. So let's just interpolate these values and find a polynomial. Okay, so we interpolate. This is the polynomial ring over Q. These are the x coordinates and these are the values, and we get x plus 1 square as we expected. So gets better and better. But there's of course a function that does it automatically for you, calling some polymake function. But the aim is that you don't know anything about, you don't have to know anything about polymake, or I guess the best would be if you don't notice that there are 4 different systems lying beneath, but for you it's just one consistent experience. Let's do a more complicated example, getting also the Galois groups into play. So let's look at a Fano simplex in dimension 6. There's a command to define this, and let's compute the Ehrhart polynomial, but already scaled by factorial 6, so it looks a bit nicer. First thing you could ask is, what are the roots? It's a bit ambiguous, so we have to tell him I want to have approximations with some precision. And then he spits out 6 complex numbers, and these are always intervals. So whenever we have floating point computations, we use intervals to have something rigorous. So these are intervals containing the root. This is the real part. This is the imaginary part. And if you look closely, this real part is -1/2 plus minus some epsilon. And in fact, this is just confirming things which are already known, namely for this Fano simplex, it's known that the real part of the root is always -1/2. This is a result by Hank and Wills. Now, let's look at a Galois group. It's not very spectacular. You just call the function Galois group, and the input is the polynomial. It has 2 return values, and the second one is not interesting for us here. And it will be a permutation group on 6 letters, as we expected. Now, this is not too enlightening if you want to, let's say, understand maybe if there are patterns, if you can somehow understand which Galois group to expect. It's more interesting to know maybe what is the isomorphism type of this group. And there's this fancy describe function which tries to give us a more human readable description of this group. And in this case, it spits out C2 cross S4. Now, then I look up this group in a catalog, and I find out it's actually C cross and the ref product of S3. Now, why write it in this complicated form using the ref product? The interesting thing is, if you repeat this computation with higher dimensions, and on my laptop I can do dimension up to 20, and it finishes within less than a minute, then you will find a pattern that you will always get such ref products, C2 cross some symmetric group. And in fact, what one can show, details will appear somewhere else, but what we can show is that using these results by Hank and Wills, that the Galois group of this d-dimensional Fano simplex, or let's say it's Ehrhart polynomial, is in fact always such a ref product, C2 ref product SK, where K is D half or D plus 1/2. Okay, so and already by just playing around with a computer algebra system which is powerful enough to compute these objects, we already found some pattern, spotted a pattern, and could prove that the Galois group has a certain form, which I think is it's a very nice result. It's a question: does it generalize? What about other polyhedrons, etc.? Okay, and so very quickly, let me say that you can also do this, play this game with more larger set of objects. So because we have access to Polymake, we have access to this PolyDB database, which has data sets for many different objects. For example, smooth, reflexive, lattice polytopes. And here we query the database to get all of them with dimension 6. So we get a handle. We want to have the specific database. And then we specify our restrictions, so dimension should be 6. And then we query the database And for each polyhedron, we compute its Ehrhart polynomial. This will take quite a few minutes because there are over 7,000 such objects. So this is not yet Oscarified. There's still some polymake syntax here, but this will get better in the future. And so what we want to do is we want to look what is the distribution of the Galois groups. So for each of these things, so we form a multiset and we push the Galois group in this multiset. So we just append it. And then we look at this tally and find out, oh, lots of them have Galois group C2 cross S4. And this raises a lot of other questions. Is this a coincidence? Is this maybe something one should expect of a smooth reflexive polytope? Is this what it, maybe this is what a random Galois group of a smooth reflexive polytope is? Yeah, all kinds of questions, but the time is up. And I want to encourage you, if you have questions, try out Oscar, or if you are curious, try out Oscar. If you have questions, talk to us. There are different ways to contact us. Here's a link, and thanks for your attention.
Thank you very much. Are there questions? Yeah.
I'm a novice at computer algebra systems, but why not make it available in Sage? Or is it already available on the Oscar?
No, it's not available in Sage. So this is a separate project from Sage. We're using a bit of a different approach than Sage when integrating the different systems. And let's say one needs a very tight integration between these different components to make this performant. So I'm not going too much into details, but the way we integrate the system, it's very, it's a different approach. It's more performant, and it's not clear if this would be possible easily in Sage, this easily.
Right. I had a similar question. I mean, maybe you could elaborate about the, you just started doing that, but elaborate about the different philosophy that you see with Sage, for instance. I mean, apart from the fact that it's using Julia rather than Python or Python equivalent, is there some other philosophical or methodological differences that you could explain in a few words?
Okay, yeah, sure. So it has a bit, it's a bit, I have to phrase it to not make Sage look bad in any way, because I think Sage is a great project. One minor disadvantage using Python is that it's very slow. So if you want to do something fast, you have to do it in C. So you have to actually have two programming languages. And also, yes, but on the other hand, with Julia, we have nearly C performance. And so writing things in Julia is very fast, and it's not much slower than writing it in C. So we can actually have now a high level language where we can implement fast algorithms, and not something where already a for loop takes forever because it's interpreted like in Python. So it allows us to implement high-level algorithms very efficiently meaning with few lines of code, but it's still very fast. And can make progress rather quickly.
Okay, thank you. Are there other questions? No other question. Well, thank you very much for this very clear talk.